So I'm very excited to be here, actually, and I have to thank to the organizers for having me. So today I'm going to show you a work that I've been doing in my master's that I did with Julio Chanamé, Paula Joffre, and also Laia Casamichela. And in this work, we are studying chemical clocks in coeval stars. So first, okay. So first, I'm going to introduce you the concept of chemical clocks. Chemical clocks are abundance ratios that have been found to follow a strong relation with stellar age. One remarkable work about this is that of Paula Joffre with solar twins, in which they found 55 different abundance ratios with this behavior. And the explanation behind this behavior comes from the different timescales of the different nucleosynthetic families. So for example, we know that nucleosynthetic timescales for alpha elements are much shorter than those of neutron capture. Thus, the two processes enrich the ISM at different times, and you can expect that, for example, abundance ratios like magnesium yttrium are higher for older stars. So in the work of Paula Joffre, they found the same thing, happens for other nucleosynthetic families in comparison with neutron capture elements. So since these chemical clocks seem to be promising to derive stellar ages, different studies with solar twins look into the limitations of this method and found that there are some abundance ratios with the slopes that have a dependency with metallicity. So chemical clocks cannot be universal and have to be used carefully if you want to derive ages with them. And also studies with open clusters like the one of Laia Casamichela found that chemical clocks might be subject to radial migration. Thus, it's not straightforward to use these relations outside the solar neighborhood. Another aspect that we thought would be interesting to study is the degree of consistency of chemical clocks in coeval stars. So one might first think of open clusters as ideal laboratories for this, but we decided to use stars in white binary systems. So Keith Hawkins has already done a nice job explaining what white binaries are. So I'm just going to emphasize the fact that they can be considered as an analog to mini open clusters, but with the advantage that they span a wider range in metallicities and also in ages, which is very useful if you want to test the consistency of chemical clocks in coeval stars in a broad parameter space. So for this work, first we used a sample of 5 white binaries with Mike spectra that I analyzed with iSpec, which is an spectroscopic framework developed by Sergi Blanco Quaresma. And with this, I determined their stellar parameters and their chemical abundances. Then, in order to improve our statistics, we decided to include other white binaries from literature that have been studied with high precision. And something important to mention here is that some of these systems have been found to have prints of planet formation or planet accretion in their atmospheres. So they present some chemical variations. This enriches our work because it will allow us to test the consistency of chemical clocks, even when there have been additional factors that could alter the chemical compositions of these stars. So here you can see the color magnitude diagram of the whole sample, and also the space that they use in the log G and effective temperature space, colored by abundance of iron. And you can see that the components of each system have very similar parameters. So first, in this work, we address the chemical homogeneity of white binaries because it can give us evidence of their common origin. We found that, in fact, they have very similar compositions within 0.1 dex, which is in very good agreement with what other works have found. And also, we recovered the results of Ivan Ramirez about an extremely unique system with chemical differences of about 0.2 dex in almost all of the elements, which is very weird. And I need you to remember this system in just a couple more minutes, okay? So in addition to this, we checked the chemical homogeneity of individual abundances for the whole sample, and we compared it to what we find for random pair stars, which are shown as gray contours, okay? we found that white binaries have more consistent chemistry than random pairs, as is expected from their formation scenarios. So far, so good. These results support all the formation scenarios of white binaries that point towards them having a common origin. Thus, even when we don't know the real ages of these stars, we can assume that these systems have coeval components. So now, moving on to the important part of the work, we did the same exercise, but with chemical clocks, and we found that they are very consistent among the components of white binaries, since you can see that they follow a nice one-to-one behavior, while random pairs that are also shown as gray contours seem to be like remarkably more dispersed. And now is when I need you to remember that very inhomogeneous system that I mentioned before, which is marked with a black square in these plots. And here you can see just a few of the clocks that show that even when the components of this system have chemical differences of about 0.2 dex, these abundance ratios tell us that the components should have very similar ages, which is consistent with the ages that Ivan Ramirez derived for these stars, which are of about 6 gigayears. Even though not everything can be perfect, sadly, and this is not the exception, since our sample is a compilation of many systems from literature, there are some systematics affecting our chemical clocks. And this is because they have been studied with different methodologies, different line selections, and different, for example, hyperfine structure treatment. So this might explain why we observe a tendency to lower values for the chemical clocks with barium, for example, and also why clocks span like a wider range in abundances in comparison to those that Paula Joffre found in their work. So this tells us that if you want to use chemical clocks to derive stellar ages, you must be careful with the way that these abundances were derived. So finally, to quantify the degree of the consistency of chemical clocks, we derived their Spearman coefficients for each of the panels in the previous figure, and we plotted their distribution here, and this is what you can see in this figure. The distribution of the coefficients for white binaries is shown in in orange, and that of random pairs is shown in blue. So you can see that the distributions found for chemical clocks are very different from each other, because, for example, the one for random pairs peak at 0.1, while the one for chemical clocks peak at 0.8. And moreover, the areas covered by each distribution almost do not overlap, which means that there is like a very low chance that stars that do not necessarily have a common origin can have the same chemical clocks. And if chemical clocks were just reflecting abundance ratios, their one-to-one correlation should be comparable with the correlation found for individual abundances, which is the one in this panel. So our results imply that chemical clocks are even more consistent, therefore, and they do not only trace chemical homogeneity among white binaries, but they also trace age information as well. Moreover, since they also have this dependency with metallicity and are sensible to radial migration, as I mentioned in the introduction, they must also carry information about the chemical evolution, which might be different at different places in the galaxy. So in addition, since our sample included some systems with chemical variations caused by different mechanisms like planet formation or planet engulfment, these results helped us to confirm the idea that chemical clocks are sensitive to the age of the stars, regardless of the possible differences in the compositions, and still be consistent with the components of such coeval systems. So given these results, we thought about how chemical clocks could be useful for other purposes besides deriving stellar ages, and we realized that they might be useful when trying to identify groups of stars that were born together. So we proposed them that using them in the attempts of chemical tagging might be useful. So to summarize, what I want you to remember of this talk is that stars in wide binary systems have very consistent chemical composition, which supports the idea of them having a common origin and having similar ages. And also that after using wide binaries to study chemical clocks, we found that they are very consistent in wide binaries, even more than in random pairs. Thus, they really carry clean information about stellar age, regardless possible differences in their chemical compositions. Also, we found that chemical clocks are even more consistent than individual abundances in coeval stars. And for that, we propose that including chemical clocks in chemical tagging efforts might improve the identification of stellar groups, since only individual abundances may be prone to present some contamination from random stars. So yes, that's everything. Thanks.
Awesome, thank you so much. Very, very exciting stuff. Any questions for Francisca? See lots of clapping. Any questions in the room? I think people are typing questions most likely. So I will ask while thinking. So this is really interesting. Can you remind me sort of what the primary elements that you use for chemical clocks, and have you explored playing around with clustering algorithms with these different elements and compared them to the performances of other elements that are traditionally used in chemical tagging?
Yes. Well, we tried all the chemical clocks that Paula mentioned in her work. And also I've been playing with some clustering algorithms, and I found that in fact chemical clocks can be helpful in chemical tagging, but not to replace individual abundances, but to decontaminate the groups that you find. Okay, so I've been like working in this, and I've run like 3 different models, and one of them included individual abundances and also chemical clocks. And what I find is that the clustering does not improve at all if you compare it with only using individual abundances. But when you use chemical clocks to decontaminate the groups that you have found with individual abundances, that actually works very, very well. So now I'm going to like use more data and see what happens.
Very cool and very exciting. We also have some questions now. The chat is blowing up. We have some questions. Okay, so from Melissa, we have, I saw in the paper you had a section on the condensation temperature trend. Could you comment on what you found there?
Yes, so as I mentioned before, there were some systems that had these prints of planet formation and planet formation or engulfment, sorry. So the trend of condensation temperature can tell you that information. So what I did was to see if there were other systems in the sample that also presented this trend, and see if more stars had these signs of accretion or anything. So that was just an exercise to see how the differences in the abundances of some elements can affect the chemical clocks. And what I found is that just they seem to not be so sensitive to those variations. So it was just like an exercise.
Cool, great, thank you. We also have a question from Sarah Martel asking, the co-moving pair that Keith showed this morning that have very different abundances, Krios and Kronos, I think are their names, are they an exception to the behavior you see?
No, I don't remember that system specifically, so maybe it's not an exception. The only exception, and the one that I mentioned in the presentation, is the system of Ivan Ramirez, which is HIP I don't remember the number, but it's in the paper. You can see it there. But I don't remember the system that you're mentioning, the one of Krios and Kronos. Sorry.
That's okay. We also have a question from Paula asking, can you comment on how you dealt with the systematics of the different abundance methods, considering that you took the data from the literature?
Yes, so that's something difficult to answer. We have discussed a lot about this with Paula and with Laia, and we just got to the point that since we are using stars that have similar stellar parameters, these systematics in the systems themselves might not affect their abundances. So you can see the same systematics acting in the same system, okay? So the correlation that we find should not be affected by these effects. But what can be in fact altered is the dispersion along the length of the one-to-one line, okay? So what we should do is to, in fact, test this and see how chemical clocks change using different methodologies, okay? That's the only way to really be able to identify how to improve this problem.
Absolutely, that's a great point.